In this video, we formalize the mathematics of the Lagrange multiplier method for constrained optimization. So it's important to always keep in mind what the task is for these methods. If we have a function we want to optimize, and we have a constraint, g of xy equals some number, so an equation that limits our choice of x and y, then that is a constrained optimization problem. We can then try to see if the Lagrange multiplier method is going to be a way to help us solve for those optimum points of our function. So in the method, what we set up is the constraint itself. In some sense, that's an element that has to be there because we need to pick x and y's that satisfy that equation. But the other element here is at the optimum, and there might be multiple optimum, then the gradient of f is parallel to the gradient of g. And just tidy that up a little bit. Where do we see that? We see that one vector is equal to a constant times the other vector. And that's how we define parallel vectors. This lambda is chosen to represent the L in Greek letters for Lagrange. So the Lagrange multiplier is that lambda. It could have been a K, it could have been a C, but because the historical connection here is to Lagrange, we use the Greek letter lambda. Now, how does it work after that? Well, we set up these equations and we start solving for the points x and y, just like we do with the critical point analysis. And once we get the values, we take the x, y values that we get and we plug them back into f. And the largest value will be the maximum on the constraint, and the smallest value of f that we get back will be the minimum. That's usually the easy part. The more challenging part is solving with those equations. If we look at two variable functions, what we can do is translate our gradient. Remember, the gradient of f is just a package of the x partial derivative and the y partial derivative in two variables. And what that means is, if we expand the first equation was the gradient of f equals lambda times the gradient of g. Well, what we can do is just take the x components of that and then take the y components of that. That translates to the x partial derivative of f is the same as the x partial derivative of g with this lambda multiplier involved. And likewise, the y partial with f equals a y partial with g, again with that lambda multiplier involved, and then we have the constraint itself. And what we see here is that we have three equations and three unknowns, x, y, and lambda. So in principle, we should be able to identify solutions to this. No guarantees because they're nonlinear equations, but at least we seem to have enough information to get some progress in interesting examples. Note that you can expand this out to having more variables. You simply add one more equation, say the z derivatives are equal except with the lambda multiplier, and then we'd have four equations and four unknowns. So this generalizes quite nicely to multivariate functions. It's most interesting though if we actually see it in action. We'll do some examples in the upcoming videos.